The mass number, also called atomic mass number or nucleon number, is the total number of protons and neutrons in an atomic nucleus. Because protons and neutrons both are baryons, the mass number A is identical with the baryon number B as of the nucleus as of the whole atom or ion. The mass number is different for each different isotope of a chemical element. This is not the same as the atomic number, which denotes the number of protons in a nucleus, and thus uniquely identifies an element. Hence, the difference between the mass number and the atomic number gives the number of neutrons in a given nucleus, n equals or z. The mass number is written either after the element name or as a superscript to the left of an element symbol. For example, the most common isotope of carbon is carbon-12, or 12C, which has 6 protons and 6 neutrons. The full isotope symbol would also have the atomic number as a subscript to the left of the element symbol directly below the mass number, 12, 6e. This is technically redundant, as each element is defined by its atomic number, so it is often omitted. Mass number changes in radioactive decay. Different types of radioactive decay are characterized by their changes in mass number as well as atomic number, according to the radioactive displacement law of Fajans and Soddy. For example, uranium-238 usually decays by alpha decay, where the nucleus loses 2 neutrons and 2 protons in the form of an alpha particle. Thus the atomic number and the number of neutrons each decrease by 2, so that the mass number decreases by 4. The result is an atom of thorium-234 and an alpha particle, 4,2He2+. On the other hand, carbon-14 naturally decays by radioactive beta decay, whereby 1 neutron is transmuted into a proton with the emission of an electron and an antineutrino. Thus the atomic number increases by 1 and the mass number remains the same, while the number of neutrons decreases by 1. The resulting atom is nitrogen-14, with 7 protons and 7 neutrons. Another type of radioactive decay without change in mass number is emission of a gamma ray from a nuclear isomer or metastable excited state of an atomic nucleus. Since all the protons and neutrons remain in the nucleus unchanged in this process, the mass number is also unchanged. Mass number and isotopic mass. The mass number gives an estimate of the isotopic mass measured in atomic mass units. For 12C the isotopic mass is exactly 12, since the atomic mass unit is defined as 1/12 of the mass of 12C. For other isotopes, the isotopic mass is usually within 0.1 U of the mass number. For example, 35 centiliters has a mass number of 35 and an isotopic mass of 34.96885. There are 2 reasons for the difference between mass number and isotopic mass, known as the mass defect. The neutron is slightly heavier than the proton. This increases the mass of nuclei with more neutrons than protons relative to the atomic mass unit scale based on 12C with equal numbers of protons and neutrons. The nuclear binding energy varies between nuclei. A nucleus with greater binding energy has a lower total energy, and therefore a lower mass according to Einstein's mass-energy equivalence relation E equals mc2. For 35 centiliters the isotopic mass is less than 35, so this must be the dominant factor. Relative atomic mass of an element. The mass number should also not be confused with the relative atomic mass of an element, which is the ratio of the average atomic mass of the different isotopes of that element to the unified atomic mass unit. This weighted average can be quite different from the near-integer values for individual isotopic masses. For instance, there are 2 main isotopes of chlorine, chlorine-35 and chlorine-37. In any given sample of chlorine that has not been subjected to mass separation there will be roughly 75% of chlorine atoms which are chlorine-35 and only 25% of chlorine atoms which are chlorine-37. This gives chlorine a relative atomic mass of 35.5. Moreover, the weighted average mass can be near integer, but at the same time not corresponding to the mass of any natural isotope. For example, bromine has only 2 stable isotopes, 79Br and 81Br, naturally present in approximately equal fractions, which leads to the standard atomic mass of bromine close to 80, even though the isotope 80Br with such mass is unstable. References Further reading, Bishop, Mark. The Structure of Matter and Chemical Elements. An Introduction to Chemistry. Chiril Publishing. PA 93. ISBN A978-0-9778105-4-3. Retrieved July 8, 2008 A.